Okay. All right. So if there are no questions, let's continue on where we left off. So what we're going to do now is to, um, okay, let's look at that real quick. Let's see, the triple integrals, question number 2. So we have the integral from 1 to e, integral from 1 to e, integral from 1 to e of 1 over x, y, z, and see, we're doing dx, dy, dz. So dx, dy, dz. Okay, so the first time around, we're going to integrate in respect to x. Okay, so if we integrate in respect to x, we're going to have the integral from 1 to e, integral from 1 to e. All right, 1 over yz is a constant, so we just pull it out. Antiderivative 1 over x is going to be the natural log of x evaluated from 1 to e. We're going to have dy dz. Okay, so we're going to have the integral from 1 to e, integral from 1 to e, 1 over yz. When we put in e, we're going to get 1. When we put in 1, we're going to get 0. So we can kind of just ignore this because it's going to be 1 times that. So it's just going to give us the expression back. So next, we're going to integrate in respect to y. So we're going to have the integral from 1 to e. 1 over z is a constant. Okay, so antiderivative of 1 over y is going to be the natural log of y, evaluated from 1 to e. And we're going to have dz. Well, we evaluate this from 1 to e is just going to be 1. So we're going to have the integral from 1 to e of 1 over z dz. If we integrate that, that's going to be the natural log of z, evaluate from 1 to e. If we evaluate at e, we get 1. Evaluate at 1, we get 0. So we get an answer of 1. Okay. Any other questions? All right. So next, okay. So let's move into what we left off at. So today we're going to deal with the dealing with triple integrals in cylindrical and spherical coordinates. Okay. All right, so let's start off first dealing with cylindrical. All right. So when we're dealing with cylindrical coordinates, we're looking at a function that is in the terms of r, theta, and z. Okay. So cylindrical coordinates are basically just an expansion of the polar. So in polar coordinates, which is r and theta, when we put it in the 3D aspect, which is going to create this cylinder, this is where z comes into play. Okay. So when we're dealing with this, we do need our polar coordinate conversions. So we have that x is equal to r cosine of theta. Y is going to be r sine of theta. Now, as far as z is, it's itself. It's z. Okay, there's no changeover for that. Also, we have that x squared plus y squared equals r squared. And we have that the tangent of theta is equal to y over x. So if we are looking for the triple integral over our region of the function f of r theta z dv, okay? Now, in place of dv, the order goes as follows. It goes dz r dr d theta, okay? So we traditionally do it in this order, okay, when we get ready to integrate. All right. So next, let's talk about spherical. So with spherical, we're looking at the function in terms of rho, phi, and theta. Okay. We're looking at a function in terms of rho, phi, and theta. All right. So we have that r is equal to rho times the sine of phi. X is equal to r cosine of theta, which is the same thing as saying that it's equal to phi times the sine of phi, excuse me, rho times the sine of phi times the cosine of theta. So basically what happened here is we took this and plug it in place of r. Y is equal to r sine of theta. And that's basically converting it from rectangular to polar. Now we're going to do it from polar to spherical. So now it's going to become rho sine of phi times the sine of theta. Z is going to be equal to rho times the cosine of phi. And then we have that phi is equal to the square root of x squared plus y squared plus z squared. But we can replace x squared plus y squared with r squared. Okay. And let's define each of these. The symbol here again is rho, and I spelled it wrong. It's RHO. Okay. And this represents the distance from P to the origin. And P is going to be it's kind of I'm trying to think of a good way to say it. It's not necessarily a point on the curve. Let me give a little bit better definition of P real quick. And P represents a point in space, and I'll show that. Yes, this is RHO. Okay, and P basically represents a point in space, and I'll show that a little bit more detail when I go through the example that we have in here that I have in the notes. Phi, PHI. This is going to be the angle that OP makes with the positive z-axis. Okay, and typically with phi is bounded between 0 and pi. Okay, phi is bounded between 0 and pi. Right, now phi is based off the y, is based off being in the YZ plane. Okay, phi is based off of being in the YZ plane. And then our last one is theta, and I'm just going to read from the notes, is the angle in the cylindrical coordinate, and it's based off the angle being in the XY plane that's formed. Okay, so what I want to do is to just first start off just taking a look at evaluating, doing some evaluations, and then we'll take a look at how we would set up different integrals. Okay, so first example that we have is this. We have the integral from 0 to pi, integral from 0 to theta over pi, then the integral from negative square root of 4 minus r squared to 3 times the square root of 4 minus r squared. We're going to do z, dz, r, dr, d theta. So the first time what we're going to do is to integrate in respect to z. So we're going to have the integral from 0 to pi, and then we're going to have the integral from 0 to theta divided by pi. And that's a rough looking theta, but it is theta. Okay, so if we integrate z in respect to z, we're going to end up with 1/2 z squared. And then we're going to evaluate it from negative square root of 4 minus r squared to 3 times the square root of 4 minus r squared. Then we're going to have r, dr, d theta. So if we plug in the upper limit first, we're going to have 1/2 times. All right, so if we plug this in, we're going to have 9 times 4 minus r squared minus, if we plug this in, we're going to have 4 minus r squared, r, dr, d theta. So now we're just going to clean this up. So it's going to come to integral from 0 to pi, integral from 0 to theta divided by pi. So if we combine like terms, we basically are going to have 1/2 times. We're going to have 36 minus 4, which is going to give us 32. Negative 9r squared plus r squared is going to give us a negative 8r squared. And we're going to multiply by r, dr, d theta. Any questions so far? Okay, so we're basically going to have this. So the integral from 0 to pi, integral from 0 to theta divided by 2, theta divided by pi of 16 minus 4r squared. And it's times r dr d theta. Okay. So now I'm just going to multiply the r through, and then I'm going to integrate. So we're going to end up with 16r minus 4r cubed dr d theta. So if we integrate this in respect to r, we're going to end up with 8r squared minus r to the fourth, evaluated from 0 to theta divided by pi. And then we're going to have d theta. Okay. All right, so the nice thing is that if we plug in 0, we're going to get 0, so we don't have to worry about the lower limit. So all we got to do is worry about plugging in for the upper limit. So we're going to have the integral from 0 to pi. And then we're going to end up with 8 theta squared over pi squared minus theta to the fourth over pi to the fourth d theta. So now we're just going to integrate this in respect to theta. So if we do that, we're going to have 8 over 3 pi squared times theta cubed minus 1 over 5 pi to the fourth, theta to the fifth, and we're going to evaluate it from 0 to pi. Once again, if we plug in 0, we're going to get 0, so we're not worried about that. We're just going to plug in the pi. So if we do that, this is going to be pi cubed times this, which is going to give us 8 pi over 3 minus this. If I plug pi in here, this is going to give me pi to the fifth times this expression, which is going to be pi over 5. And if we do the calculations and get a common denominator, we should end up with 37 pi over 15. Any questions? Okay, so let's look at the next example. All right, so our next example, we're looking at the integral from -1 to 1, integral from 0 to 2 pi, integral from 0 to 1 plus cosine of theta. And we have 4r dr d theta dz. Okay, so as you notice here, we can have it in a different order than what it is traditionally. All right, so if we take a look at this, so first time we're going to integrate in respect to r. So if we integrate in respect to r, what do we get?
Two r squared.
Okay, so we're going to end up with 2r squared, and we're going to evaluate from 0 to 1 plus the cosine of theta, and we're going to have d theta dz. Okay, so the nice thing is that if we plug in 0, we're going to get 0, so we don't have to worry about the upper limit. We just got to worry about the lower limit. We just got to worry about the upper limit. So if we do that, we're going to integral from -1 to 1, integral from 0 to 2 pi. So we're going to have 2 times 1 plus cosine of theta, quantity squared, d theta, dz. Okay, so now we're going to square this out. And this 2, I'm just going to take it all the way out. So if I square this out, I'm going to get 1 plus 2 cosine theta, cosine squared theta, d theta dz. Now, I can integrate the first piece, the second piece. I can't integrate the third piece in its present form, but what can I use to integrate it?
That power reducing formula?
Okay, so we're going to use our power reducing identity to be able to do that. So for this one, the power reduction formula is going to be 1/2 times 1 plus cosine of 2 theta. So what we're going to end up having is this. Okay. So we're going to have 2 times the integral from -1 to 1, integral from 0 to 2 pi of, all right, so I got 1/2, so that's going to give me 3/2, plus 2 cosine of theta plus 1/2 cosine of 2 theta, d theta dz. So now I'm ready to integrate. So if I integrate, I'm going to get 3/2 theta plus 2 sine theta plus 1/4 sine 2 theta. And we're going to evaluate that from 0 to 2 pi in dz. All right, so if we plug in 0, we will get 0, so we don't have to worry about that. So all we're worried about plugging in is the 2 pi. So if we plug in the 2 pi in here is going to give us 3 pi. If we plug 2 pi into the second term, what are we going to get?
Zero.
Okay. And if we plug 2 pi into the last term, what are we going to get?
0.
We're going to get 0. So really all we have is just 3 pi in dz. Okay, so now we're going to integrate this in respect to z. So we're going to have 2 times basically 3 pi z evaluated from -1 to 1. So we're basically going to have 6 pi times 1 minus a -1, or we end up with 12 pi. Any questions? Okay, so next, let's look at our next example. Okay, so our next two examples are basically we're going to be finding, um, we're going to be integrating over a region D, and what we're going to have to do is to set up the integral in order to help out with that. Okay, so uh, the first one, what we're told is that D is a right circular cylinder whose base is a circle. R equals 3 cosine of theta, and the top lies in the plane Z equals phi minus x. Okay, so what we're going to do is to set up our triple integral over the region in terms of f of r um, theta z, and then we're going to integrate in respect to dz r dr d theta. Okay, so all we're doing is setting up the integral because we don't know what this is, so we can't integrate it. So we're going to have our triple integral of f of r theta z dz r dr d theta. Okay? So for this particular problem, okay, now what it's telling us is first we're going to start off, let's start in the back end with theta. Okay, so theta is going to be basically looking um, at the base. So the base that we're focusing on is dealing with this circle. Okay, it's dealing with this circle. Now, when we deal with this, we got to be careful and pay attention to how we're moving along. Okay, so for the base, all right, so it's r is equal to 3 cosine of theta. So it's starting out here and it's coming around, circling, coming back around. Okay, so we've got to make sure that we are able to go through the complete cycle of this. Okay, all right, so this, in order to deal with this, I've got to be careful of how we are moving. Okay, so when we're starting off with this, I want to keep in mind that I want to start and return back to replace. Okay, now kind of, and I'm saying I wanted to start off with the back. Let's not start off with the back. Let's start with the front. Okay, so the front is in terms of z. Okay, now as far as z is concerned, okay, we want to we don't want to go below. So if you think about z, what's the lowest value that you think we should go? And keep in mind that we're kind of trying to stick to quadrant one. So what will be the lowest value of z? Yes, the lowest value of z will be 0. Now, the upper value of z, okay, actually will be the function that is defining c. But keep in mind that z has to go to r. So what would the upper limit be? And let's think about this. How is z defined? It's defined as 5 minus x. But let's keep in mind that we don't have any x things in here. So is there a way for us to get rid of x? Yeah, we can change it to polar form. So what would x be? R cosine theta. So for the upper limit, it's going to be along this curve. So it's going to be 5 minus r cosine of theta. Okay. All right. Next, what we want to do is we're dealing now with r. Okay. So if you think about the radius of the circle, the radius first starts off at what? So what's the minimum r value? So what would be your minimum r value? Now, always keep in mind that r is never negative. It's always positive. So what's the smallest r value that we can have? 0. Okay, so we can start here, and then we are going to make it around. Now, as I'm going around, I'm following along the curve. Okay, and the curve is defined as what? So this curve is defined as what?
3 cosine theta.
3 cosine theta. That's the upper limit. Okay. Now, next, we've got to deal with theta. Okay. Now, the way theta is going to work is going to be as follows. We have to pay attention to how r worked. So r starts here at 0, and then r follows along the curve. Okay. So if I start here on r, what is going to be what is my value of theta? So if I start here, what value of theta will give me an r of 0? Pi over 2. Okay. And then what I'm going to do is that I'm going to go around and then return. So what value of theta will allow me to return? Well, keep in mind that still got to make this 0. So it'll be 3 pi over 2. So now, instead of going from pi over 2 to 3 pi over 2, all right, what's another way that I can represent going from starting down here to up here? So I can rename the bottom, instead of saying it's 3 pi over 2, I can rename it as what?
Zero.
No. What's another way we can rename 3 pi over 2? And let's think of it in terms of this. If I start, this is 0, but if I go in this direction, this is now called what?
Negative pi over 2.
So that's going to be our lower limit. Then our upper limit will go to what?
Pi over 2.
Pi over 2. Okay? Oops, 2, not 3. So we're going to go from negative pi over 2 to pi over 2. So here's the thing. For this particular curve, it only takes it to go through its cycle pi. Okay? It takes half the time as it would if it was a circle centered around the origin. Okay? So it takes half the amount of time. But when I do it, I don't want to use from pi over 2 to 3 pi over 2. Okay? So what I want to do is that I want to stay on basically the right hand side of the unit circle and only focus on that portion to create the base. Okay. Any questions? Okay. All right, let's look at our next example. So in this one, D is a solid, a right solid cylinder whose base is a region between the circles. So we have circle R is equal to cosine of theta, and we have that R is equal to 2 cosine of theta. This is the base, okay? And whose top lies in the plane z equals 3 minus y, okay? So again, we're going to look at doing the triple integral over the region of f r r theta z dz r dr d theta. Okay, so we're going to look at the triple integral. All right, so let's start off with z. Okay, so if we think about this, what's going to be our lower value of z? And again, keep in mind that we want to kind of stay in the first octave in a way. So what would be the lower value of z?
0.
It would be 0. Now, the upper value of z would be what? Yes, it would be 3 minus y, but again, we can't write it in terms of y. We got to write it in terms of r. So we get rid of y and replace what it is equal to in polar. So we're going to write 3 minus r sine theta. Okay. All right. So next, we're going to deal with r. Okay. R is going to be focused on the base. Well, where's the base located between? How's the base being created?
Cosine theta into cosine theta.
Right. So we're going from cosine theta to 2 cosine theta. Okay. So that's how the bases are being created. Right. So now, finally, what we need to do is to figure out how theta is going to run. Okay. Now, as far as theta is concerned, how it's going to run, this one, well, both of them are going to be kind of the dictating factor of what's going on. Okay, so when we're looking at this, you've got one circle that looks like this, and then you've got the second one. It's going to look like so. Okay, now considering how we want to do, we want to start with here and then work our way around. Okay, so if we start at 0 for r and then work our way around, and keep in mind which direction I'm going in as follows. Okay, so theta is going to start off at what?
Negative pi over 2.
Negative pi over 2. And we're going to stop at what?
Pi over 2.
Pi over 2. Okay, so just in here, and it's just because of the way we want to run, we want to make sure we start at 0 for r and then work our way out. Okay, so that's why we're starting here and then going around counterclockwise. So you have to remember that everything is now, we're starting off the negative and then working our way to the positive. Any questions? Okay, so next, let's take a look at dealing with the spherical coordinates. Okay. So our first example, we're just going to do an evaluation. So we're going to take a look at the integral from 0 to 2 pi, the integral from 0 to pi over 4, and then the integral from 0 to 2 of rho times the cosine of phi times, write this a little bit better, times rho squared sine of phi, d rho, d phi, d theta. So the first time what we're going to do, we're going to integrate in respect to rho. All right. Well, before I do that, I'm just going to go ahead and multiply things out. So I'm going to have the integral from 0 to 2 pi, integral from 0 to pi over 4, integral from 0 to 2. We're going to have rho cubed, cosine of phi, sine of phi, d rho, d phi, d theta. So if we integrate this in respect to rho, what are we going to have? So if we integrate in respect to rho, what will we have?
Root to the power 4.
Okay,
4.
so 1/4 rho to the 4th. Then we have cosine of phi, sine of phi. We're going to evaluate that from 0 to 2, d phi d theta. Okay, now if we plug in 0, we're going to get 0. So we don't have to worry about plugging in it. So all we got to do is plug in 2. So if we plug in 2, what value do we get for here?
Eight.
We're going to get what?
8, right?
Are you sure?
It's going to be 4, my bad.
Okay, much better. So we're going to have 4 times the cosine of phi, sine of phi, d phi, d theta. Okay. Any questions there? All right, so now we're going to integrate in respect to phi. And to integrate in respect to phi, we're just going to do we're going to use a u sub. So we're going to say that u is going to be the sine of phi, du is going to be the cosine of phi. Okay, so what we're going to have is this. So we're going to have the integral from 0 to 2 pi. So if we take the antiderivative of u, well, that's going to be 1/2 u squared. So we're going to have 4 times 1/2 u, which is the sine of phi. We're going to square that, and we're going to evaluate it from 0 to pi over 4, and then we'll have d theta. So we're looking at the integral from 0 to 2 pi of 2 sine squared theta, evaluated from 0 to pi over 4, d theta. Now, if we plug in 0, we're going to get 0, so that's nice, so we don't have to worry about the bottom. Now, if we plug in pi over 4, well, what's the sine of pi over 4? Okay, square root of 2 over 2. But if we square that, that's going to be what? 1/2. So basically, we're looking at the integral from 0 to 2 pi of 2 times 1/2 d theta, or the integral from 0 to 2 pi of just d theta, because we know this is going to be 1. Well, if we take the antiderivative, we're going to end up with theta evaluated from 0 to 2 pi. And what's going to be our answer? 2 pi. And there you go. Any questions? Okay, so let's do another one. And this time it's going to be just similar to what we did with the cylindrical, in that we switch the orders of how we integrate, just to show that it is possible to do. But most of the time we try to keep everything in the traditional format. So for this one, we have the integral from pi over 6 to pi over 3. Then we've got the integral from cosecant of rho to 2 cosecant of rho. Then integral from 0 to 2 pi. I mean, not rho, though, so phi, sorry. Then we've got rho squared sine of phi d theta d rho d phi. So the first time around, we're going to integrate in respect to theta. So we're going to have the integral from pi over 6 to pi over 3, integral of cosecant of phi to 2 cosecant of phi. All right, so if we integrate in respect to theta, we're just going to end up with theta times rho squared sine of phi. We're going to evaluate that from 0 to 2 pi. And then we're going to integrate in respect to d rho, then d phi. Now, again, the nice thing here is if we plug in 0, we're going to get 0. So we don't have to worry about the lower limit. If we plug in just the upper limit, we're going to end up with just 2 pi times rho squared sine of phi. Then we have d rho, d phi. Okay, so next, what we're going to do is we're going to integrate in respect to rho. So if we integrate in respect to rho, we're going to have the integral from pi over 6 to pi over 3. Okay, so what would the antiderivative be?
1 over 3 rho cube.
Okay, so we're going to end up with 2 pi thirds rho cubed times the sine of phi. Evaluate it from cosecant of rho to 2 cosecant of rho d phi, and to 2 cosecant of phi d phi. You say the variables correctly. So essentially what we're going to do is I'm going to factor out the 2 pi over 3 and the sine of phi and then evaluate. So if I do that, this is what I'm going to have. All right, so I'm going to have the integral from pi over 6 to pi over 3. And I'm going to have the 2/3, 2 pi over 3 sine of phi times. If I put in the upper limit, I'm going to end up with 8 secant cubed phi minus, if I put the lower limit in, I'm going to have cosecant cubed phi. And I'm going to integrate in respect to phi. Okay, so next, I have the integral of pi over 6 to pi over 3. So basically, if I clean this up, and if I do that, I'm basically going to end up with 14 pi over 3. Then we're going to have the sine of phi times the cosecant cubed of phi. So d phi. Okay, so we can clean this up a little bit more. Okay, so if we can clean this up a little bit more, so we're going to have the integral from pi over 6 to pi over 3. We're going to have the 14 pi over 3. If we multiply these together, we're just going to end up with the cosecant squared of phi d phi. D phi, not d theta. Now, if we take the antiderivative, right, what's the antiderivative of cosecant squared? Negative cotangent, good. So we're going to have negative 14 pi over 3 times the cotangent of phi, and that's going to be evaluated from pi over 6 to pi over 3. So I'm going to have negative 14 pi over 3 times. Now, if I find the cotangent of pi over 3, I'm going to end up with the square root of 3 over 3 minus, if I find the cotangent of pi over 6, I'm going to get the square root of 3. So it's going to be negative 14 pi over 3 times, if I simplify this, it's going to be negative 2 times the square root of 3 over 3. And then my final answer would be 28 square root of 3 pi over 9. And this will be our answer. Any questions? Okay, so at this time, let's take a 10-minute break, give your brains a chance to catch up and everything and rest a little bit. And then we'll move into our last set of examples and how we're going to do those problems and everything. Okay? Okay, we'll get started in just a couple more minutes. Okay. Okay, sorry for the delay. All right. So next, what we're going to do is we're going to take a look at the first problem we're going to take a look at is to take a look at how we would set up the triple integral in spherical coordinates and how it will change if we change up the um, the order of how we're going to integrate. Okay, so for this problem, it says D is uh, let D be the region bounded below by the cone Z equals the square root of x squared plus y squared, and above by the plane Z equals excuse me, Z equals 1. Set up the triple integral in spherical coordinates that gives the volume of D using the following order. Okay, so first of all, what we're going to do first is we're going to represent um, the base. Okay, so when we are doing this, and we are doing more of this for the aspect of it being in the um, YZ plane. Okay, and the reason why we're focusing primarily on the YZ plane is because of the fact of how we are going to find phi. Okay, so first of all, what we're going to do is to look at that plane. Okay, so we're going to say this is the y-axis and this is going to be the z-axis. Okay, all right, so if we're dealing with z is equal to the square root of x squared plus y squared, okay, so, and we are also told that z is equal to 1. Okay, so z is equal to 1. Basically, what it's doing is setting up this straight line here. Okay, up at the top. Now, for the other one, if z is equal to 1, basically what we have is we're going to be dealing with the circle. If z is equal to 1, we're going to be dealing with the circle that's centered at the origin and has a radius of 1. So let's say this is 1 here, and this is 1 here. So we're dealing with this circle right here. Okay, and it's a rough looking. It's not quite as smooth as I wanted, but kind of gives us the idea. Okay, all right. So now what we're going to do is to set things up. Okay, so for A, we're going to do the triple integral. And as far as part of the formula is concerned, as far as volume is concerned, we are going to have the rho squared sine of phi. And the order we're going to do the first time is going to be d rho, d phi, d theta. Okay, so let's start off with dealing with um, the rho. Okay, so if we're taking a look at this, okay, so let's keep in mind that this line here is equals 1. Okay, and now what I'm going to do is I'm going to connect a line from the origin to connect to that line. Okay, so the circle here represents, okay, and let me do some side work here so you understand where I'm coming from, how I'm getting this. Okay, so z equals the square root of x squared plus y squared. And we know that z is 1. So we can say that 1 is equal to the square root of x squared plus y squared, or 1 is equal to x squared plus y squared. Okay. Now, as far as x squared plus y squared is concerned, we can say this is 1 is equal to r, and that would be the formula in terms of polar coordinates. Now, we know that r is equal to rho times the sine of theta. Okay. Now, in place of r, we are going to put 1. Okay. We know that z is equal to 1. And we are given a formula for z. We're told that z is equal to rho times the cosine of theta, and that's equal to 1. Okay, so we can write an equation for rho. So rho is equal to 1 over cosine of theta, which is the same thing as secant of theta. Okay. I'm sorry. Wrong angle variable. It's not rho. I mean, it's not theta. It's phi. Okay. All right. So what we're going to be looking at is this. Okay. So in order to come up with what phi is going to be, okay, so phi is going to be the distance from a point on the curve, okay. It's the way we have phi defined. It's the angle that is, the way we have rho defined. It's the distance from the origin to P, and we're going to call this P. So it's the distance from here to here. This is rho. Okay. Now for this distance, okay, and let me mark it. We're going from here to here. Now for that distance, the distance first starts off at what? So we're starting here. We're going to start off with the distance of what? Of 0. Okay. Now we're going along this line here. Okay, we're going along this line here. So what we need to do is that rho has to be going along that line. Well, if we look at the information we have, keep in mind that rho is trying to get up to where z is equal to 1. So do we have rho defined for this line based on the information that I've got provided so far? Yeah, so rho is going to be secant of phi. So that's going to be the upper limit. Okay? Any questions there? Okay, so next, what we want to do is we're going to set up phi. Okay, now phi is going to be the angle that OP makes with the positive z-axis. Okay, so OP, which is this line to here. This is going to be phi. Okay, now let's think about it. If we start off, essentially we're starting off at what value? And keep in mind that it has to be between 0 and pi. So we can say that, and think of it that this is the bottom now. So I'm going from the bottom and this is the top. So if I start off the bottom, I'm starting at an angle measure of what? Of 0. Then I'm going to this. So how much of an angle am I going to create?
Pi over 4?
Yes, it's going to go to pi over 4. Okay, and here's the reason why it's going to be pi over 4. Okay, so, and let me just switch over to a page. All right, so what I'm going to do is pull out the triangle that I have. Okay, now we know it's going to be a right triangle. We know that the length of the top one was 1. okay? And the length of the side also is going to be 1. So essentially what we have is a special right triangle. So it's going to be a 45, 45, 90 triangle. So the angle that we're looking for is from here over, because this represents the positive z. So that angle is 45 degrees, or pi over 4. Does that make sense to everyone? Okay, so now let's go back. All right, so the last thing we're going to take a look at is that we need to deal with theta. Okay, we need to come up with the values for theta. Now, for theta, okay, let's think about this. If we shove this down into the xy plane, okay, so if we're looking in the xy plane, keep in mind that we are dealing with a base that is a what? So the region is bounded above by a cone. If you condense the cone into the xy plane, it now becomes a what? So this is what you have in the 3D. Now, if I shove this down, it becomes, yes, a circle. And it's going to be a circle that is centered where? At the origin. So this is basically what we're going to have. So let's think about this. If I'm trying to go around this circle, I'm going to start off at what? So I'm going to start off at 0, and then as I make my way around, I'm going to come back to what? 2 pi. So that's going to be my limits of integration for theta. Okay. Any questions there? Now, typically for theta, theta's really easy to do, okay? Because if you when you push it into the xy plane, a lot of times it'll be a nice common shape, like a circle, or it may be a portion of a circle. So it's something nice, okay? Any questions there? Okay, so now let's do a part B. Okay, so for part B of this, we're going to do the triple integral, and we're doing rho squared sine of phi. And this time we're going to integrate in order of d phi, d rho, d theta. Now, as far as this is concerned, okay, we know the limits of integration for theta, which are going to be what? Because it's not going to change since it's the same region. So theta is still going to be what? From what to what? Yeah, it's still going to be 0 to pi, 2 pi. That's not going to change. All right, so now the other pieces are going to change. Okay, and we need to take a look at those. Okay, so for this, all right, so now I need to do my drawing again. And again, keep in mind that I am in the YZ plane. Here's one, here's one. Okay, so we've got this line here. We've got this portion here. Then we've got this going on here. Okay, so this time, okay, so the first thing we're going to integrate in respect of is phi. All right, and phi is going to represent the distance from, it's going to be based on the angle OP that OP makes with the positive x-axis. Okay, now here's P. Okay, here's O. All right, so here's our issue now. Okay, so we're going to have something that deals with this. So we can deal with this portion here. But now we also have to deal with swinging this to this. Okay, so what's different this time is that as far as the segment is concerned, we now have this piece to work with, and we have this piece to work with. Okay, now that we have two different pieces, are we able to do this all with one integral? And another way for me to ask this is that, can I say that this entire piece will follow the exact same angle measure all the way? So can I say that the two different color shades, if I move those pieces, are they going to follow the same angle? No. So since those two different pieces will not follow the same protocol on things, that means we have to set up two integrals in order to get this to work. Okay, so what I'm going to do is, all right, the first part is fine. So now what I'm going to do is I am going to add in a second integral. Okay, and let's not have this so close together since I've got to put in the limits of integration. And it's still going to be same thing. So it's going to be rho squared sine of phi d phi d rho d theta. Now, d theta is still not going to change. We're still going to go from 0 to 2 pi. That's still going to happen. Now, for the first part of d phi, okay, so we start off the angle at what? So if this is the bottom, the angle is going to start off at 0. And then we're going to go up to z, which is going to be what? Pi over 4. Okay. Now, for this piece here, when we start, we can't say it's 0. Okay. This piece here has a different name. Okay. And what we need to do is we need to take a look at how we're going to name this. Okay, so remember that we said that rho times the cosine of phi was equal to 1. And that's what this piece is representing. But since we're integrating in respect to phi, we need the limits of integration to be in terms of phi. And let me actually write my things in the correct place. Pi over 4 goes here. Now, for this other piece, this needs to go away. Okay? So this lower limit needs to be something in terms of phi. Yes, in terms of phi. So if I want to solve for phi, what should I do first? So if I want to solve for phi, what should I do first?
Divide by row.
I'm going to divide by rho, so I'm going to have the cosine of phi is equal to 1 over rho. Now, how will I get phi by itself?
By cosine inverse.
Okay, so phi is going to be the cosine inverse of 1 over rho. Now, that's what this is starting out at. Then I'm going over. So what would that angle be for me to go over? And don't think it's a bigger angle. It's the same angle. It just has a different start. So the angle still, even though it's way out here, the angle measure is still the same. It's going to be what? Pi over 4. Yes, it's still going to be pi over 4. So what we're going to do, our start, since it's a different piece, is not going to get to be 0. It has to be, and it's because of the fact that this piece here is outside of this circle piece here. Okay, so we're going to go from the cosine inverse of 1 over rho up to the angle, which is going to be pi over 4. So the bottom piece is dealing with it as, okay, this is part of the figure. The top piece is kind of outside the figure, so we have to give this piece a new name, but it's still following the same path to get to the z, z-axis, the positive z-axis. Okay? All right, so now the next bit is going to be dealing with rho. Okay, so rho is going to represent the distance from P to the origin. Now, let's keep in mind that as far as rho is concerned, you've got a path here, and you also have a path here. Now, let's deal with the bottom path. Rho, the distance first starts off at to be what? So when it starts, the distance is going to be 0. Then I'm going to get to the circle. I'm going to hit the circle or the base of the cone. So from to the base of the cone, well, how far have I gone? Keep in mind the cone base is here. And what's the radius of this base? It's 1. So we're going to go from 0 to 1. Okay. Now, for the next piece, we're going to start at the edge of the base and go forward. Okay. Now, from the edge of the base, what are we at? Will row be? So, what did we say this was initially anyway? We said it was 1. Now we're going to go out to the end here. Okay. So, let's think about this. All right. It's a right triangle. So, we need to find the complete length. All right. So, we know this is 1, 1. So, what would be the length of the hypotenuse? Square root of 2. Okay. So, from here to here, our final distance is going to be what? The square root of 2. And there you go. So, as you can see from this problem, you can see that by by just switching up the order of the coordinates can sometimes create kind of a nightmare to get the problem set up. And you may have to do different pieces of it. Any questions? Okay. All right. I do have 2 more examples in this section, and I don't want to try to rush through them. So I will start with those on Thursday. Okay. And that will finish up our last little bit of this. And then we'll move into the next section and deal with how do we do transformations between different coordinates. Okay. Any questions?
So can you go over how you got rho square sine phi, like for the integration?
That's part of the formula for volume.
Oh, okay.
Okay. So just like with in the polar coordinates, like when we were saying if you do the double integral in terms of dx dy, when you convert it over, it becomes the double integral r dr d theta. That r is part of the formula. Same way happens with the when you're dealing with switching from rectangular coordinates of dx, dy, dz, and we want to switch it to, say, spherical. It becomes a triple integral of the region, and then the rho squared sine of phi is part of the formula. And when we talk about the transformation in the last section dealing with triple integrals, I'm going to show you how this comes about.
All right, I see.
Okay.
Thank you.
Mm-hmm. Any other questions? Okay, so one thing real quick. Let's see, quiz. Yes. Okay, so don't forget that quiz 14 is available and it's due Thursday. Okay, and I think I've got all the solutions up and available for you, up through the triple integrals. Up through triple integrals in using cylindrical and spherical coordinates.